right, team, let's get started. So these are the board notes for today. I'm just going to write board notes so that way when I scan it, you guys know what they are. And this is the 12th. All right. So we are going to talk redox today. That was, for those that have taken level 2 chemistry, the last standard we did last year. So we finished the year on redox. What do we remember? Oh, what's on that piece of paper? Oh, I need to collect your weekly check-ins. I'll do that later. Oxidation and reduction. Oh, actually, let me go over. So we are doing the redox internal. So that way you guys have this information. It is worth 3 credits. Fortunately, a lot of these chemistry standards aren't worth much. If you're looking it up, it is Chem 3.7, and the AS number is 913. I think it's 93 on the top of my head, but I'll double check that for you guys. So when we are talking about redox, redox is a broken down word to talk about 2 different types of reaction. And Xander's got an idea of what those 2 reactions were. The first one is your reduction, and the second one was your oxidation. Questions so far? All right. There are lots of different definitions on what we think about when it comes to oxidation and reduction. Back in the day, historically, what a lot of scientists notice is that chemical reactions often involve the use of oxygen, and they realize that, oh, oxygen can be added to reactions or removed from reactions. That definition got more and more refined as we discovered more and more about atomic chemistry. Eventually, we got to the point when we realized that with these redox reactions, we are seeing some sort of transfer of electrons. So when we're thinking about reduction, we are thinking about a gain in electrons. When we are thinking about oxidation, we are talking about a loss of electrons. Now, just as a reminder, these 2 need to go hand in hand. We have to have both involved in a redox reaction, because when we are thinking about the loss of electrons, this lost electrons go to the reduction reaction. So that's how we are not creating or destroying matter. What just happened? Just turned off. So that's how we're not creating or destroying matter. Are we okay with that so far? Sorry if I'm going a little fast. Let me know if you want me to slow down. All right, so let me show you what I mean. So for example, if we are burning sodium, Na, in chlorine gas, you will make sodium chloride, which is our table salt. This is an example of a redox reaction. I'll write the names in case you guys want some refresher. So that one here is sodium. This one's chlorine. And then that's sodium chloride on the other side. Do you guys want to see a video to see what this reaction looks like? Yeah? Okay. Let me see if I can find you one. All right, so hopefully that video kind of helped you visualize what's going on with those 2 reactions. And obviously we have a chemical reaction going on. It is very different compared to what we had as our starting material. So the starting material that we had here was sodium. That's a gray silver metal. It is very soft and easy to cut. You can cut it with a butter knife. However, it is very, very reactive, which is why it's being stored in something like hexane. Because if you drop that sodium into water, it's going to react with the water itself. So it doesn't react with hexane, so that's why it's being stored in there. But potentially a very dangerous metal on its own. If you ingested it, it would probably react with the water in your body and cause an explosion, I would assume. So it's crazy to think that that plus chlorine gas, which also is very, very toxic, that this has been used in the war as a war agent. Very poisonous kind of gas. You don't want to breathe that in. But together, these two react together and form sodium chloride, which is something we use every day in table salt. So kind of crazy that alone they are quite problematic, but together every day. He talked about ionic bonds, which it is true that is an ionic bond. If we think about level 1 science, we talked about how atoms want to gain or lose electrons to fill their valence shell. So when we look at sodium on the periodic table, it has one valence electron, which it wants to get rid of, to drop down a shell and be stable. Chlorine, on the other hand, has 7 in their valence shell. They just want to gain 1 electron to become stable. So we've talked about that transfer of electrons, but now for redox, we talk about the transfer of electrons in a little bit more depth and understanding kind of why and what is going on. So what we're going to do is we're going to pull this reaction apart so that way we can look at it as the individual components to understand what redox is. So the first one we'll look at is oxidation, which is with our sodium. Did I make sure I started the recording again? I can't remember. Yes, I did. Okay. So if I was to pull this apart, I would have Na becoming Na plus. So this is my half equation if we are looking at it. I've basically just taken this ionic compound and I've split it into half. Sodium is 1/2, chloride is the other half. Now I've already started to color code this one as oxidation because what I would see here is that we are losing electrons. I've gone from having no charge to being charged. So I've lost 1 electron. So that is the loss of an electron. Now, one of the little things that we learned about last year to help us remember oxidation and reduction was Leo the Lion says gur. The other one is oil rig. Oopsie. Oil rig. So, loss of electrons, oxidation, gain of electrons, reduction. Or in this case, oxidation is loss, reduction is gain. So really important that we get these the right way around so that way we're using our vocabulary correctly. So in this case, I see that I've lost an electron. So this is an oxidation reaction. Now, the good news for this year compared to last year is that the redox equations are going to be very simple for this year. We're not going to be worrying about those complex ones that we talked about last year that balance the hydrogen and the water and the oxygen. We're just going to be focused on these really basic ones. All right, keep going. Okay. Some other things to keep in mind when we're looking at this is one of the other things we talked about last year was oxidation numbers and to check to see how oxidation numbers have changed. I'll start talking about them now just because it'll help build in that content for when you have to do your justifications when you're doing your writing up. So the other thing to keep in mind with oxidation is that we have oxidation numbers. These we assign to the components that are involved in the chemical reaction to help us figure out what has been oxidized and what has been reduced. In this case, for this year, you're not going to need it as much as last year because there's not going to be as many things in there. But the way, and there's only really 2 rules that you guys need to remember for this year. Last year there was maybe about 5 or so. The first one is that if anything is in an elemental form, the oxidation number is 0. So 0, sorry. And then the other thing to keep in mind is charged particles. So whatever the charge of the ion is going to be the same oxidation number. So this oxidation number is +1. is equal to the charge. So in this reaction here, I have the oxidation number of sodium going from 0 to +1. So if I see an increase in my oxidation numbers, that is oxidation. And this should parallel what's happening with the electrons. So in this case, if there's an oxidation number has increased by 1, so we have therefore lost 1 electron, which we can see in our equation over here, that 1 electron has been lost. Hopefully this is ringing a bell to you guys. Good news is, like I said, we're not going to have to go into as much depth as last year, but you're going to be learning some other stuff instead. Anything you need me to rewrite or explain? Monoatomic. That's supposed to be an O and then an A. Are we good? Yeah, if you didn't. Yeah. Keep that there and I'll move on to the next page. All right, should I keep going? Good? Okay, just checking because I don't want to go too fast. All right, now let's split up the other half of this equation. So in this why do you keep turning off? Oh, because I'm not using you. That's right. I need to change the settings on this. All right. So we had chlorine, Cl2, and this is becoming chloride, the ion, which is Cl-. I will give you guys a resource sheet that will have information to tell you what the redox pair is. So don't fret too much about where I'm pulling this information from. All right, now one of the things we have to keep in mind when we're looking at this equation here is that it's not balanced. We need to balance it. So if we're looking at this one here, I see my chlorine has a 2 behind it. Remember that 2 behind applies to everything in front. So basically for a chlorine molecule, there's 2 chlorine atoms there. I need to make sure that on the other side we also have the same number. So I need a number 2. In this case, because I'm now talking about not a formula, I need to put that 2 in front. So we don't put the 2 behind in that case. It's all about chemistry language. So I have 2 chloride ions. Are we okay with that? And why I decided to do that? All right. Now, next thing we got to think about then is what's happening with our electrons. So we want to balance the charge. In this case, we see how this was no charge, and that actually its oxidation number is equal to 0. This side here, the oxidation number is equal to its charge. The charge is -1, so its oxidation number is also -1. So I can see here already that there's been a decrease in oxidation number. So that tells me that's reduction. The next question then is thinking about how many electrons did it gain or lose. In this case, because we're talking about reduction, we have gained electrons. That's got 2 negative charges, so I must have gained 1 electron for each chlorine atom. That's why I put 2 electrons on that side. So we have gained electrons, therefore we have reduction. And in fact, there is 1 electron gained for each is the important word, chlorine atom. So since I have 2 chlorine atoms, each one is gaining 1. Are we okay so far? Yes, no? Sort of. All right. Let me just show you guys some on the checklist in case you're starting to freak out and worry about these equations. So, being able to define oxidation and reduction with reference to gain or loss of electrons, that is an achieved requirement. So being able to go through and say that I recognize this is oxidation, it is gained lost 1 electron, this one is reduction, it is gained 1 electron, that would be enough for the achieved. So we've covered that criteria. And then the next one here is writing the half equations. So these here are examples of half equations. That one and that one. So if you can write our half equations, that's a merit level requirement. But we'll do some more practice on that. All right, the last requirement here is to write full redox equations. So let me show you what that means when we're writing our full one. So when we are looking at these 2 equations here, we want the electron numbers to match and we want them to be on opposite sides. We want them to be on opposite sides so they cancel out, and we want them to have the same number so they cancel out. So one of the things to keep in mind when I'm trying to put my full equation together is that I might need to multiply one of these 2 equations so the electron number matches. So in this case, since the electron number is 2, this also needs to be multiplied by 2. Let me show you what I mean. All right, so when I look at this guy over here, this has a 2, that only has a 1, so I need to multiply this whole equation by 2. So that becomes 2, that becomes 2, and that becomes 2. Now when I put these 2 equations together, the electrons will cancel out. So we have 2 sodiums plus Cl2 makes, you can write it as 2Na plus 2Cl minus, or you can write it as 2NaCl. And that's now talking about that full equations. That's the excellence criteria. Sorry, gotta keep waking up the computer. Do you guys want another example? All right, I'll give you 2 more examples and then I can give you some practice questions. So, all right, let's do another example. Let's say I was starting with magnesium chloride and I'm making magnesium and chlorine gas. Are we okay with that so far? All right, let's pull this apart so I can figure out my redox equation. So when I look at magnesium chloride, this is an ionic compound, so each half of these things will be charged. Chloride, I remember, has a -1 charge, and I have 2 of them. So magnesium must be a +2 to balance that out to 0. So we have Mg2 plus becoming Mg, and then we have Cl minus becoming Cl2. All right, so when I look at that first equation up there, I see that my oxidation number is +2 and it's gone down to 0. So there's a decrease in oxidation numbers. I can see my charge has gone from having a +2 charge to having no charge. So have I gained or lost electrons? Gained them. Because you see how I'm going from positive to nothing. How many did I gain? 2. So I'm showing that on this side here. Gain 2 electrons. Yeah? So is that oxidation or reduction in that example? That is reduction. Oh, I forgot. I've already given you chlorine as an example. I should have just chose a different molecule. Or not molecule, another particle. All right. So we see how this is not balanced. So I'm putting a 2 in front. Now I see that the oxidation number has gone from -1 to 0. The one above went from +2 to 0. I also see that this had a negative charge, and now that negative charge is gone. So did I gain or lose electrons? I lost. So they're going to be on this side. How many? 2 total. Is that oxidation or reduction? Oxidation. How many did each chlorine ion lose? 1. Each chlorine. Gotta watch our language. 1. Yeah. All right. Do you want another example? Or you feel like you're okay? Feeling okay? Just trying to check. We end at 25. Huh? We can do practice. So I have some choices for you guys. I've made a GIM kit. I don't know if you guys remember GIM kit from last year, but it has all the oxidation and reduction revision if you guys want to just do that. And it integrates in some gameplay. So it's like online, kind of like Kahoot, but better. So you can play GIM kit. I'm happy to write you guys a list of questions. Yeah, those are choices. What do you feel like? You're so shy. So quiet. Okay, before we go on to GIM kit or practice, do you guys want some more time on this, I'm guessing, to review it? Okay, so that means then the next lesson we'll just focus on this sort of stuff. All right, I have the GIM kit made, so let's play the GIM kit, I think. And I think it's probably going to be a little bit easier.